All right, hello everyone. So today I'm going to be going over KD trees and alongside KD trees, the find nearest neighbor function. So first I'm just going to talk about what a KD tree is, how you make it, and then I'm going to go into how you, or at least how I think about KD trees geometrically. And then finally we're going to talk about how you can use KD trees to find the nearest neighbor of some query that might not be in the tree. So to start off with, a KD tree is sort of like a binary search tree. So in a binary search tree, it's a binary tree. So basically you have nodes, and every node has at most two children. And each of these nodes will store a point. In a binary tree, um, you have the property that all the points on your right subtree over here have value greater than the point stored uh, in this node up here, in this sort of root node. And all the points in the left subtree have value less than that node. So for example, if this was a 5, stuff that can go in the left subtree can be stuff like 4, 3, 1, -2, 0, stuff like that. Stuff in the right subtree is anything bigger than 5. So 6, 10, 20, 100, any value greater than 5. And what this allows you to do is this allows you to like search the tree. So because if you're looking for something and it's bigger than 5, it has to be on the right side. So that's sort of the reason why these binary search tree and these properties of having oh, that's not what I wanted to do. And these properties of having values on the right that are bigger and values on the left that are smaller are sort of good. So figured out how to do it. So when it comes to storing things that are higher dimensional, and this is where the KD comes from, the KD in KD tree stands for k-dimensional, we need more than just one way of comparing the points. Because you can see here, for example, um, 3, 7, and 5, 3, you have the x-coordinate is the x-coordinate in 3, 7 is less than the x-coordinate in 5, 3, but the y-coordinate in 3, 7 is greater than the y-coordinate in 5, 3, which means you can't just use this sort of greater than less than comparison when it comes to comparing points or objects, things with more than one dimension. That's where KD trees come in. So KD trees conceptually are very similar to binary search trees. You're going to have, or like structurally, so you're going to have a node up here. You're going to have maximum 2 children. And each of these nodes here is going to store a point. So in this case, for example, it would be a 2-dimensional point. The one difference from a k-dimensional tree and a binary search tree, though, is the k-dimensional tree will actually care about another input called the dimension. And the dimension is just whatever current dimension you pick that you want to compare the points on. And what that allows you to do is at every level of the tree, you can pick a dimension and you can pick a pivot point. And I'll show you what that looks like with an example. So for example, here I have these points up here at the top that I want to make a KD tree out of. And let's say for my first node, my root node, I want to pick the x dimension to split on. So I'm going to use x and y to refer to these just because it's 2D. If you have more dimensions, you'll also commonly see the dimensions written out in numbers, so 0, 1, 2, 3, stuff like that. But for this case, x and y are going to be easier just because it's easier to visualize in the coordinate plane. So let's say I'm splitting on the x dimension, and let's say I arbitrarily choose my pivot point up here to be, I don't know, let's say we want it to be 210. So let's put in 210 up here. And yeah, this is, bear with me, this is a little bit, you know, since I am drawing everything out as I go, um, the art might not be the best. Let's say I have 210 over here, and let's say I decide to split on my x dimension. What that means is on the right side are going to be all points that have x coordinate greater than 2. Because I'm comparing the points strictly on the x dimension. So like the binary search tree, we're extending this by, instead of comparing points on multiple dimensions at once, we're going to be comparing the points at different dimensions on different levels. And we're going to use that structure in order to create this sort of binary search tree structure, considering more than one dimension. So 210 is actually a bad example. So I'm going to go ahead and undo that. I'm going to pick another point, perhaps. And let's say I pick the point, let's see, what do I want? Say I pick the point 6, 1. This point is nice and in the middle. And again, I'm comparing the x dimension. So on the right side is going to be all points that have x coordinate greater than 6, 1. On the left side is going in the x dimension. And on the left is going to be all points that have x dimension less than 6. So concretely here on the left subtree, we're going to have the points 3, 7, 4, 9, 2, 10, and 5, 3. And on the right side, we're going to have the point 7, 4. And just going to be a single point, because there's only one point that's greater on the x dimension. Right? So we're done with the right subtree. There's only one point here. This is going to be our leaf. But there's still some more work to do on the left subtree. So here, I'll keep a sort of built-out structure of what our tree looks like over here, just because I predict the drawing is going to get a little messy. So we're going to have 6, 1 at the roots, and then we're going to have 7, 4 over here. So in general, this works for any pivot point you choose. At any level, you can choose whatever pivot point you want. But similar to like a binary search tree, there are points you can pick on each level that will sort of give the tree an overall nice structure. And if you've learned about binary search trees, you might know what I'm trying to get at. But let's finish building the tree first. So let's say on this level, I just decide to pick the point 3, 7 as my root that goes here. So now like my subtree is going to have a root of 3, 7. And again, I need to deal with the left children and right children of 3, 7. So because my previous level, the level where I chose 6, 1, this was being compared on the x dimension, this time I'm going to compare on my y dimension. So what that means is I'm going to, in the right, I'm going to put points in that have y dimension greater than the point I chose, which is 3, 7. So I'm going to put in the points on the right, 4, 9, and 2, 10, because those are both points with greater values in the y dimension. And then on the left, I'm going to have the points 5, 3, because this is the only point with y dimension less than 7. So in my final tree, I'm going to pick the point 3, 7 here, just because that's what I decided to pick as my pivot. Again, this is just arbitrary. And then since 5, 3 here is just a leaf, I'm going to put the node 5, 3 over here. And over here, I need to do one final step. So again, let's say, in this case, let's say I pick 4, 9 to be my root node for this subtree, this right subtree. So that means I'm going to have 4, 9 over here. And which side of the tree should 2, 10 go on? Well, because this first dimension was compared on the x, and the second dimension was being compared on the y dimension. So remember, I was only considering the x dimension for this the first split to decide which points went on the left and right subtrees. For the second split, I was only considering the y dimensions for which points went on the left and right side of my chosen like subtree. In this case, because I finished looking through all the dimensions, I'm going to just loop back around. So here now I'm going to compare from the x dimension again. And because 210 has lesser x value than 4, 9, I'm going to put 210 on the left like that. And so this is how I would construct my KD tree. So you can see here, like from the root node 6, 1, since this was compared on the x coordinate, all of the points in the right subtree, so in this case it's just one singular point, but all the points here have x coordinate greater than 6 because I'm comparing on 6. All points on the left, all of these points you see in the left subtree, have x coordinate less than 6, right? And then if I look at my 3, 7 subtree, this was compared on the y coordinate, which means that all points to the right, 4, 9, and 2, 10, all have y coordinate greater than 3, 7. And the singular point to the left, or the entire left subtree, in this case just 1 point, will have y coordinate less than 7, right? And then tiebreakers, you can decide how to handle. In this case, I intentionally made it so there were no tiebreakers, just so we didn't have to worry about that. But you can decide to put them on whichever side of the tree that you want. And then again, for 4, 9, since now we're back to comparing the x dimension, which means that the right subtree, which is empty, if there were points here, these would all have points x coordinate greater than 4. On the left, we only have this 1.210, and it has x coordinate less than 4, because we're comparing on the x dimension. So yeah, I probably, reiterated a lot of stuff a lot, but I just want to make sure that it's clear what we're doing, how we're making the split. Remember, the points I'm choosing to split around are arbitrary, but once I choose a point to split around, the points that I'm going to find in my left and right subtree are determined. So I just want to make sure that that is clear. Okay, so that's how I would construct my KD tree just by picking arbitrary pivot points. But this is not, this is not a very nice KD tree. In binary trees, we have this concept of being balanced, which intuitively just means your tree looks symmetrical. One side isn't too long, and the tree overall has a very nice structure. So the way we do that, similar to how we could make a binary search tree balance, is instead of picking an arbitrary pivot point or an arbitrary point to make our subtree point, we would always pick the median on that specified dimension. So what do I mean by that? So when I made my first split, remember originally I picked the point 6, 1. This is not a good point because this would put 1, 2, 3, 4 points on the left subtree and only 1 point on the right subtree, right? Again, I'm just comparing my x dimensions here to find how many would go on each side. And that's not a great split because it doesn't really split my data evenly. On the other hand, if I looked at all the x coordinates, I have 3, 4, 2, 5, 6, 7. If I pick the median point instead, which in this case I'm just going to say is 4. If I pick the 4, 9 point instead, remember this is being split on the x dimension. On the right side, I'm going to find the points 3, 7 and 2, 10. And on the left side, I'm going to find the points 5, 3, 6, 1, and 7, 4. And the reason this is nice is before I had 1 point on one side and 4 points on the other side. This was a difference of 3 nodes, which is a lot. But now my two sides have approximately the same number of nodes. I have 2 on the left and 3 on the right. And if I keep doing this process, I would find that my KD tree actually becomes balanced, which means that, again, like intuitively, it has a very nice structure. And in terms of runtime, this actually guarantees that you have like an O of log n time to sort of search for something if that thing is in the tree. Or it'll tell you if the thing is in the tree or not, and you can do that in O of log n time, because now the height of the tree is bounded. I'm not going to get into that too much, but that's why we like having things balanced. And if we do this repeatedly, we're going to find that the end tree is always balanced. So keep in mind here, like I'll just draw out the final tree on the right again. So we have 4, 9 at the top. I have no children yet, or I have no leaves yet, so we have to do a bit more work. But here, remember, now instead of splitting on the x dimension, I'm now splitting on the y dimension. So I'm going to find the median, which doesn't really matter on the left side. But because I sort of rounded down up here, I'm going to round down again. I'm going to say like my subtree is 210. Yeah. So again, here I'm determining that the median is 10. Or no, sorry. It should be, yes, I think the subtree should be 3, 7 actually. Yeah. So because I rounded down choosing the median up here when I was splitting on the x dimension, I should also round down in my second level when I'm picking the median of the y points. So in this case, rounding down, I get that the median is going to be 3, 7, which means that 210 is going to be on the right side of that. So that's going to give me over here my left subtree of 4, 9 is going to look like this. I'm going to have 3, 7 as the left child, and I'm going to have 210 as the right child. Again, this doesn't actually matter too much, but as long as you're picking like the median, um, however you choose to do the type breaking is going to change the overall structure of the tree too much. But on the left side, so I have the points 5, 3, 6, 1, 7, 4 here. Now remember I'm splitting on the y, and I want to find the median y value from the remaining points here. The median y value, the y values I have are 3, 1, and 4. The median of that is going to be 3, which means I'm going to make my node 5, 3. That's going to be my subtree root node. And now if I do the same splitting on the y, on the left I'm going to see the point 6, 1, and on the right I'm going to see the point 7, 4. And now, and this is my completed tree. So I have 5, 3, 6, 1, and 7, 4. And that is our completed KD tree. The first point was split on the x-coordinate, so it has the same properties as the KD tree we talked about before. But now instead of just having one like subchild on the right and a very long tree, sort of subtree on the left, now we have this sort of well-behaved tree where none of the subtrees go too deep. So that's the construction of a KD tree. Now we'll sort of talk about how that looks geometrically. So I'm going to cut this out, and I'm just going to quickly draw in these points on the XY plane. All right, so just bear with me for a second. I'm not great at editing, so I'm not going to try to edit this part out, but you can go ahead and skip forward if you'd like. Okay, so those are my axes. I have 1 point at 3, 1, 2, 3, 4, 5, 6, 7, 1 point at 4, 9, point at 2, 10, 5, 3, 6, 1, and 7, 4. All right, so here are my points, right? And then, okay. All right, so here are my points. So my first point that I'm splitting around is the point 4, 9. So I'm going to draw that in a different color. So 4, 9 is this point right here, right? So what I'm doing is I'm splitting this point around the x-axis, right? Which means the points 5, 3, 6, 1, and 7, 4 are all to the right of 4, 9. They're all in the right subtree, right? And those points in the coordinate plane are these points right here, right? Similarly, the points I have in my left are 3, 7, and 2, 10, because these points have x less than 4, 9. Or sorry, just x less than 4. And those are the 2 points right here. So what I'm actually doing is I can imagine I'm drawing a vertical line through 4, 9, where all my points in my right subtree are going to be found on the right side of this divider, and all my points on the left subtree are going to be found on the left side of this divider, because all the points on the right have greater x, and all the points on the left have lesser x. So if I draw this line x equals 4, my right subtree is all going to appear on the right of this line, and my left subtree is all going to appear on the left of this line. Okay, so hopefully that makes sense. So now on the second level, we're splitting on the y. So on the left we have this point 3, 7. So 3, 7 is this point right here. And what I'm doing is the property here that's being followed is all points that have greater y are going to be found in the right subtree, and all points with lesser y are going to be found in the left subtree. Right, so here I can draw a horizontal divider line, and all points in my left subtree would be found above this line, and all points all points in the right subtree would be found above this line, and all points in the left subtree would be found below this line. Because I'm splitting on y, the line is going horizontally instead of vertically. Hopefully that makes sense. Okay, and then here I'm technically splitting on the x again for the final point 210. But because there's no more points in the grid, this doesn't really give us any extra information. For the right subtree, we have the next pivot point is 5, 3. So that one is this point right here. And yeah, the points are sort of close together, so it's a little hard to see. But again, it follows the same property that all the points on the right subtree are going to have greater y, because this is being split on the y dimension. And all the points on the left subtree are going to have lesser y, which means I can draw, if I draw this horizontal line again, I can see that all the points on the right side of the subtree are going to appear above this line, and all the points below it are going to appear, sorry, all points on the left subtree are going to appear below this line. So hopefully that makes sense. And then again, if I really want to be a completionist, I can draw these vertical lines through the final 2 points. But again, this doesn't really give us any extra information, which means, yeah, so they don't really matter that much. Maybe they do. I'm not sure. Okay. Anyways, that's not really that important, but hopefully you understand the overall geometric structure of what a KD tree looks like. So hopefully you might have seen this diagram before. I know when I saw it first, I didn't really know what it meant, but hopefully this sort of clarifies why these lines are here, how you get these lines, and all of that. Okay, so now we'll actually talk about nearest neighbor. And for nearest neighbor, I'll talk about it purely conceptually. So I'll actually get rid of all of this. Cut, yes. I'll get rid of all of this, and I'll also get rid of all of this. That's not the right one. Okay. Okay, so for the find nearest neighbor, there are a couple decisions you have to make. So number one, our find nearest neighbor function is going to be a recursive function. And the definition of this function is going to be, all right, so I'll type this out. So the nearest neighbor function. So this is a function that, given a subtree of the KD tree and a query, find the points in the tree closest to that query. So remember, this is going to be find the point in the given subtree, right? We have to specify subtree here because this is a recursive definition. So the tree passed in is not always going to be the root when we recurse. But this is going to be our general recursive definition. So let's say, for the sake of argument, that we have a point in the KD tree here. This is going to be our subtree, right? And let's say the subtree in the KD tree was split on the x dimension, right? So what that means is we can sort of imagine this vertical line passing through it, where the, if this is a subtree, and this is like right, this is left, the right subtree would be found over here on the right side of the line, and the left subtree would be found over here on the left side of this vertical line. Right, so again, this is just conceptually what we talked about before with the KD tree geometry. And let's say my query point is here. So I'll name this point Q. Right? Okay, so first I have to decide, well, which side of the subtree, so given the subtree, which side of the subtree should I look on to find the point closest to that query? And this is, well, just because, and this is like a pretty simple decision to make. Because the query point is on the right side of this line, we probably want to look on the right half of the subtree because there's a higher chance that there's a point closer to here, that there's a point close to the query because it's on this side of the border. So we're going to recurse in this case on the right subtree, right? And let's say we find that the nearest point is, I don't know, right here, right? So let's say like this is the current best. So this is the current best point that the recursion found from looking on the right half of the subtree. Okay? All right. So if this is the current best point, then that means if there were any point better than current best, it would have to be inside of the circle of radius, with radius like the distance between the query and the current best. So I can imagine the circle being drawn around around query of radius like this distance here. Because if I know that if I have any other point, in order for it to be better than the current best, it has to lie inside this circle. right? In higher dimensions, you can imagine like a ball, and it would have to lie inside that ball. But the point is, it has to have a smaller distance um, to the query than current best, which means it has to lie inside the circle. And we note that this current best has to be the current best that we found from looking in our right subtree. And this is because we need to trust the recursion, right? We recursed on the right subtree, which means given the recursive definition, we have found the point in the right subtree closest to the query, which means we have found the closest point on the right side of this divider to query. Like there's no other point on the right side closer to query than this current best point we found here. So now once we finish the recursion, we go up. Maybe like the original split point, like the original subtree point is better, in which case we select that point instead. But that's sort of a simple decision we have to make. The other decision we have to make is, do we have to recurse on the left? And the reason we might have to recurse on the left, well, in this case, we don't have to recurse on the left, right? Because the circle lies completely inside the right subtree, and we know we found the best point in the right subtree, we know current best has to be the point closest to the query. Because basically we have all the information about the right subtree from our recursion. So now I have to decide, do we have to look on the left side? So yeah, in this case, we don't have to, because there can't be any point in the left side that's closer to query. Because any point in here will definitely have a distance greater than the distance from current best to the query, right? But there are some situations where this isn't necessarily the case, right? So for example, if this is my subtree, and I'll draw my query again in blue, and I'll draw my current best in red again. If I'm in a situation like this, where I have a circle and it overlaps with and it passes into the left side, in this case, I know all the information about this side of the circle. I don't know any of the information about this side of the circle because I didn't recurse on the left. So in this situation, we want to recurse on the left. Similarly, we could have a point where we are tangent to the line. So I'll just draw the circle first so it's easier for me. Let's say this is the query. Let's say this is the current best. So in the situation where it's tangent, we also want to recurse on the left because there's a chance that like this point here could be our best point as well. But in the case that we see up here, where the circle lies entirely on one side of the line, we don't have to recurse on the left side because we know there's no possible way anything on the left side could be better than whatever our current best point is. So now the question is, how do we determine which one of these three cases we're in? So this is not a live class, so I don't know what your first intuition is. But I have heard some people give intuition about like connecting the connecting the query point to the subtree point, which I think is a good start. So if we like connect this point on all three things, we can maybe look at like what information we can get. So the problem with this is connecting the query point to the original point in the original subtree point does not actually give us that much information because we don't actually care where the current point is on this line. The current point could be here, very close to the circle. It could be all the way down here. But regardless of that situation, like regardless of where the current point is in all three of these situations, we know the overall diagram doesn't change, right? These diagrams are going to look the same because we only care about the line itself and the circle. Where the subtree is, like where the subtree point lies on this line, does not matter to us because the overall diagram still looks the same. So what we actually care about is we care about this circle and we care about this line. And we know that in one of the cases where we want to recurse, so again, that's these two cases, we know at some point the line crosses the circle, right? And we know that in the case where we don't want to recurse, the line doesn't cross the circle. So if we can figure out like how we can calculate whether or not a line crosses a circle or not, we will know in which situations we want to recurse on the left side. So how do we actually do that? Well, I have the radius here, right? I have the radius of the circle. And I know that a line crossing the circle means that at some point, the distance from the radius to the line, or sorry, the distance from the query to the line will be exactly the radius, right? In the tangent case, that that point is exactly the tangent point. But there are an infinite amount of points on the line. So how do I actually determine, like, I want to have a foolproof way of choosing a point such that I can calculate its distance from the query point and determine whether or not the line at some point crosses the circle. Hopefully that makes sense. Like here, for example, I want to pick any of these points in this section because these points will have distance less than my radius, which tells me that this line, like if I draw, for example, the line from here to here, this line is going to be less than my radius because my radius goes from, well, it has this little extra tail here, right? So I want to be able to pick like a point inside, like on this section of the line. And I need to be able to guarantee that it lies on that section of the line if this line passes through the circle. Same here, except in here, it's even more strict. I have to pick exactly this point so I can determine whether or not the circle touches the line. And we know that if there is some overlap, if there is a point where the distance from the point to the line to a point on the line is equal to the radius, then if we were to draw the perpendicular distance, which if you remember from geometry is the shortest distance from a point to the line, then we know that this distance will have to be, this distance is less than or equal to the distance from this point to the point on the line that makes it like equal to the radius of the circle. Hopefully that made sense. So basically the whole idea is instead of trying to calculate like points on the line where our radius is less than or equal to the radius of the circle, what I can do is instead I can calculate this perpendicular distance here. And this perpendicular distance is going to be the smallest distance from my point to my line. If this perpendicular distance is less than my radius, I know that if I were to draw the perpendicular radius, I would have this little tail over here in cases where I cross the line. If I'm perfectly tangent, then this perpendicular distance is going to be exactly my radius. And if I'm not touching at all, this perpendicular distance is going to be strictly greater than my radius. So I can use this perpendicular distance to calculate whether or not my circle crosses the line. And if it crosses the line, I know that I have to recurse on the left. So hopefully that made sense. In order to calculate the perpendicular distance, so remember like our original point has some like x coordinate, like x1 comma y1, and our query has like I'll call it xq comma yq. Right? If I want to calculate the perpendicular distance, what I can, like all I care about is, in this case, because I split x1, y1 on the x dimension, all I care about is the horizontal distance from x of my query to the x of my points. Because all the points on this line, including this point here that I'm actually calculating the distance to, are going to have the same x coordinate as the point I split around. If I were splitting on the y dimension, they would have the same y coordinate as all the points on the line would have the same y coordinate as the point I split around. So if I want this horizontal distance here, all I have to do is I have to take the absolute value of xq minus x1, the horizontal distance from my query point to my to the subtree point, like the point I split around, and I'd have to square that. And yeah, that'll give you my square distance from here to here, or like from here to the line, the query point to the line. And I can calculate the radius of the circle because I have both of these points, and I can just use the distance formula for that. Here I'm squaring this just because I want to use square distance, because square rooting will lose me some precision. Um, but yeah, hopefully that made sense. In this situation, where this is like less than the radius, less than or equal to the radius squared, I know I want to recurse on the other side of the subtree. And that is how the nearest neighbor algorithm works intuitively. So hopefully that made sense. It was probably a bit of a long-winded explanation, um, but hopefully you found it useful, and hopefully that allowed you to understand KD trees a little bit better. Thank you.